ANSYS Simulation Lecture 12, Flow Simulation using Fluent. In this problem, we'll introduce the structure of Fluent flow simulation and using this water flow in a pipe example. First of all, we load the software, ANSYS, and then enter ANSYS Mechanical, ANSYS Workbench. And in the project schematic interface, we will drag Fluent procedure onto geometry. And we'll enter mesh. This will be ANSYS mechanical interface to define mesh and inlet, also outlet surfaces. So first of all, we define inlet surface, and I strongly suggest that you name the inlet, name the outlet. Of course, you can name anything, but it is easier for yourself. So if we create the name selection here, we will name it inlet, and this is the inlet. So name this surface, create name selection as outlet. So we have created two surfaces with names, inlet and outlet. Just as I said, you can name it anything, but naming it this way will be most easy for yourself. So update the mesh, and then we finish with this procedure and go back to schematic interface. Now we'll enter Fluent at this point, and at this page you have to define whether you have parallel processors in your computer or whether it is double precision, and we can simply click OK for the default, and then we enter Fluent interface. And if you have experiences in SolidWorks flow simulation or COMSOL flow simulation, there are 6 steps in which you can follow for the solution of a flow problem. The first step will be drawing of a geometry and opening a problem, and also define the inlet and outlet. For the second step, called initial conditions, you can define whether there is heat or viscosity or radiation or other, for example, acoustic or solidification, etc. And for the second step, you also define materials and cell zone, whether the volume will be running water or air. So from models up to cell zone conditions will be the second step, and we name it initial conditions. And the third step begins here, boundary conditions, up to reference values, and this is the third step. For the fourth step, we begin here, solution method, up to monitors. The monitors is actually the goals. You set the goals for the problem, and this is step 4. Step 5 start here, up to here. This is step 5, and step 6 result. So this is step 1, step 2, 2, 2, 2, step 3, 3, 3, 3, step 4, 4, 4, step 5, 5, 5, step 6. Okay, so we go back to step 1. Step 1 gives you a chance to check the problems and to look at the meshes or the geometry. You can display the meshes and change colors if you want to. So you can look at what you have up to here with meshes and geometry. You can also define whether it is a absolute or relative velocity formulation, or whether it is a pressure-based or density-based problem. You can also define whether it is a steady state or transient problem. and you can define gravity for it, and you can change unit if you want to. So this is step 1. For step 2, the initial condition, we need to define that the volume is with air or water. So for the models, we can define whether it is a multi-phase problem, whether heating problem is involved, whether the fluid is viscous or not, or whether some other species is involved, or there's a discrete phase or solidification and melting involved in it. So this is a choice of models involved in the flow simulation. And for now, we have a most simple case where a single phase water flows through a pipe. So we accept all the defaults for the models. And for the materials, the default fluid material is air. So we have to increase or create a water material. So we enter Fluent database and choose water here, liquid water, and copy it onto the program and close. So we now have two different fluid. One is air, which is the default, and the other is fluid water, which we chose right here. And now we have to define the zone or the volume of the pipe. So we click on the pipe and edit the materials for it. So the default material is air, and we change it into water. So in the second step, we define that the volume is water instead of air. So we accept defaults here and increase the material of water here and define the volume to be water. So we finish with the step 2. For step 3, the inlet condition, the default type is velocity inlet. We change it into mass flow inlet, and we'll define it as the normal boundary with 0.5 kilogram per second. So we define here that the water flow in the inlet at the mass flow rate of 0.5 kilogram per second. And for outlet, it is a pressure outlet at default. So you know that it is very convenient that you name it properly. So we edit. You can see that the pressure value is 0. 0 means it is atmospheric pressure or the ambient pressure. So we don't have to change anything here. So we have finished with the step 4, which is defining the inlet property and outlet properties. And also, you can define dynamic mesh, but since there is no boundary moving in this problem, so we don't have to define dynamic mesh. And the reference values, we can take the default values. So we have finished with the step 3 up to here, from here to here. And for step 4, from here to here, we define the goal, what we need to know, what we want as the result. So the solution method will be simple, and you can change it if you want to. And the solution control, we can take it as a default. And for monitors, the monitors will be the goals in other softwares. So it will define what you like to know, what you want to know as your result. So we can increase for example, volume goal, and we can let the software calculate pressure of the whole volume for us. Static pressure for the zone, you have to click on the zone, the volume, and we'll monitor the iteration and convergence of the volume pressure in the window 2. So now we can also create a velocity volume goal or monitor, and you can monitor it at window 3 for the convergence and iterations of velocity in the volume. And also we can create surface goals. For example, we can create inlet surface goal. Since the inlet mass flow rate is known and pressure is not known, so we define the inlet pressure goal and monitor the inlet pressure iterations and convergence at window 4. We can also create the inlet pressure, inlet velocity distribution, and monitor the velocity iterations and convergence at window 5 in the inlet surface. We can also create an outlet surface a velocity, since the velocity is unknown but the pressure is known already, so you don't have to define a pressure goal for it, only velocity is unknown. So we define a velocity goal for outlet and monitor the iterations and convergence of the velocity at outlet in the window 6. So now we have finished with the goals and monitors. So we have finished with step 4. Now we have finished with all the definitions of the problems. So all the problem has well defined. So now we can enter step 5, which is the solution phase or computation phase. First of all, we will create an initial value for the calculation. So we use the default hybrid initialization and run the initialize, and this is the initialize values. And for the calculations, we can let the computer save every iteration values for us. You can choose for yourself how many iterations to save. And for the running phase, you can define how many iterations to run for this problem. For example, I'll define 100 iterations for this problem and to calculate. And in the calculation phase, you can see that the iterations is running from 1 to 10 to 15. So I have defined 100 iterations and it will stop at 100 iteration. And if you want to run another, for example, 50 iterations, you can add to it. So, and after the 100 iterations is completed, we can look at the convergence of each items. For example, we can see that whether the convergence of a global goal, for example, this is the global goal, and the second is also the global goal. One is velocity and one is pressure, and this is a surface goal. You can look at each goal to see whether it is converging. So if you are satisfied with this convergence, you can go ahead for the result. Of course, you can define result here, but for myself, I would rather display the result in ANSYS interface. So I'll go back to schematic interface and enter ANSYS CFD interface for the step 6, the result phase. For the result, we can display for example, a contour for the inlet and display the pressure of it apply. So this is the pressure of inlet, and we can also define another contour for outlet for pressure also, and also another contour 3 for pressure of the wall. So for these 3, we can display the pressure distribution of the volume, and we can also hide all these items and draw another one for the velocity at the inlet, for example, and this will be the velocity, and another for the velocity of outlet here, the velocity of outlet, and also another for velocity of the wall. So now we can look at the velocity distribution of the volume, and we can also hide all the contour plots, and so you can create a streamline of all domains starting from the outlet and go forward and backwards. 40 points and equal spaced. And the variable will be the velocity. So we apply, and this is the streamline. You can also display the animation of the streamline, but I'm not going to go into it right now. The most important thing that I want to talk about here is that you can understand the procedure of a fluent flow simulation in a 6-step model. The first step is drawing a geometry in a CAD system, and the second step will be meshing. Actually, this is the first step also, the meshing and defining inlet and outlet. And then enter Fluent. And in Fluent, there will be 6 steps. The first step will be the geometry and meshing. The second step will be the initial conditions, defining that there's water in the channel, and the channel will be running water. And the third step will be the boundary conditions. We define the inlet mass flow rate of 0.5 kilogram and outlet surface, the pressure outlet of 1 atmosphere pressure. For step 4, we define all sorts of goals. For example, global goals for the volume of pressure and velocity, and the surface goal at the inlet for pressure and velocity. And for the outlet, since the pressure is already known, we calculated velocity distribution at the outlet as the goal. And so this is the step 4. And for step 5, we define how many steps to save the iteration and how many iterations to run. And for the result, I displayed the result in ANSYS CFD post-processor. So this is the structure of the solution method in 6 steps. So this is very important that you understand the structure of the solution in these 6 steps.